It's time for machine learning. Oh boy. Here we go. The topic is linear regression. Now, first time I started machine learning and they started with linear regression, I was like, what? That's machine learning? We did that in pre-calculus and calculus. Think of this as a starting point. What I'm going to do in this slideshow is introduce linear regression. I'm going to give some mathematical details, but don't worry if you don't get the mathematical details. That's not the point. At the very end, I'm going to provide the code, and I promise you, you will be able to do the code. Okay? So this is just an overview of how linear regression is machine learning and how it works. Okay, linear regression. So given a set of data points, linear regression gives a straight line that minimizes the square of the distance between the points and the line. Traditionally, the least squares regression line was found using calculus. Calculus is used to find the minimum quite often. So let's look at a linear regression example. Here we have the median house value, which is the target, the y values on the left side. And that's what's trying to be predicted given the average number of rooms. You can see from the data that as the average number of rooms goes up, the target median house value also goes up. The blue line is the least squares regression line. It minimizes the distance between any given line and the points that you see. The shaded part is the uncertainty in that line with the 95% confidence interval. So linear regression is machine learning. Okay, why? Machine learning requires data, and in particular, a column to make predictions from that data. Linear regression predicts one column, the y value, from another column, the x value. Machine learning extends linear regression from 2 dimensions to an arbitrary number of dimensions. It's called machine learning because the model learns from new data. More data results in more accurate models and a better regression line. Okay, let's look at linear regression in 2 dimensions with some detail. We have y equals mx plus b. I've emphasized the times there because in programming, you have to put in the times. So in math, x is the input, m is the slope, b is the y-intercept, and y is the output. We're talking algebra here, graphing a straight line. Note that x may take on any value, kind of like the data points in a column. The key to finding the line of least squares is to find the right m, the slope, and b, the y-intercept. So we have y equals mx plus b, and x is the input, and we're trying to find the weights m and b to get the output y. Well, if we have m equals 2 and b equals 3, then y equals 2x plus 3. Now let's look at linear regression in n dimensions. Okay, so we start with y equals mx plus b. We can switch it to y equals b plus mx. And then we can make a change of variables to y equals b naught plus b1 x1. Okay? And these are all 2-dimensional. Well, now this is the point of the change of variables. We can add another column with another weight. So we can add b2 and x2. When we do that, we are in 3 dimensions. Furthermore, we can add another column and weight, b3 and x3. And now we are in 4 dimensions. Well, this process can certainly continue, and that leads us to n dimensions, any number of dimensions that are desired. So here's a little trick, okay? If x1 is defined as 1, then it can be written like this, okay? And that's a little bit cleaner because that's simply the summation bx, and you can even write it in shorthand like that, capital B, capital X. Now note here, I do want to emphasize the importance of the capitals because capital X does mean multiple dimensions and lowercase y here does indicate 1 dimension. So that is intentional, and it's also a norm that we'll be using with code. And again, those are all n-dimensional. Okay, so we have y equals bx. And in machine learning, x is the input, the columns, and b are the weights, the slopes. X may take on any number of dimensions. If X is 100 columns, then X contains 100 dimensions. You could say that the line is 101 dimensional. It ceases to become a line. It's actually called like a hyperplane. Okay. Now B provides a unique weight for each column. If there are 100 columns, then B is a list of 100 different values. For the final result, each value in a column X is multiplied by the weight B and summed. So I think we want to look at this in terms of data, and it'll make more sense. Okay, so here is the Boston housing data with the median house value, and along with 4 columns listed, total bedrooms, population, households, and median income. So X1 is the first column. X2 is the second column. X3 is the third column. X4 is the fourth column. And what is the last column? Well, it actually depends. In this case, it is what we're trying to predict. Therefore, it's not an X. It is a Y, okay? Because Y, that's the goal. That's the output. That's what we're trying to predict. The goal is to combine the other columns to deliver that median house value. Just to give you an example, if the median house value of the first row is 1,283, we could say, oh, multiply X1 by 1, and then all the others by 0. Okay, so what about B? Well, B1 is going to multiply all of the X1s. And that's part of the catch, right? There's one B1, okay? And it's going to multiply each row. This is why this is hard to do, because we have a lot of rows. It's actually challenging, okay? B2 multiplies X2, B3 multiplies X3, and B4 multiplies X4. And again, I don't know what these values would be here. The goal would be to get not just the first row of 66,900, but all of them, and you can look at, well, maybe it's, I don't know, 1 times total bedrooms plus 1/2 times population minus, 1/3 of households. It's not going to be like that, but something along those lines. Okay, we're choosing the right B's. And importantly, there is a B naught, okay? It's, X1 is thought to be 1 there, but, it's a small adjustment actually, okay? And so that's what you do. You add all the columns together to get the median house value. You can also see how hard this would be to do just by looking at it. I mean, it's impossible when you have millions of rows, but even with these 5, right? What would you pick for B1, B2, B3, B4? This is where programming comes in. The key is to find the right B's. Okay, so how do we choose these weights? Well, Y equals BX. The weights, also known as coefficients, are the range of values for B, right? Because remember, B, there's multiple B's here. At first try, B is completely random. After comparing the random predictions to the results, B is adjusted on whether it's too high or too low using a technique called gradient descent, which is calculus, and we are not going to learn, okay? We don't need it. It happens behind the scenes. During each subsequent iteration, B is adjusted until the error is minimized. After the error has been minimized for B, the final model is selected. Why? Because once you have all your B's, you have the equation, right? Now let's look at how it works with code, okay? So that's some theory for you, a bit of an overview. What do we actually do? Is this going to be like crazy math coding? No. Okay, here's what it is. You import linear regression from sklearn, which is a Python machine learning library. You initialize the model like this, model equals linear regression with parentheses. That sets up the model. It doesn't really do anything. Then everything we talked about, everything that I just went over in the slide is that line of code, model.fit x comma y, okay? So it's fitting a linear regression model to the data x, all the columns, so that it gets as close as possible to the output y. That's going to choose the weights. That's going to deliver the equation. Then you can score the model to see how good it is, which we will do because you want to know if your model is bad or good. And then finally, you can actually make predictions with the model. So the prediction would be like if a new line comes in, a new row, I should say, of data. And then for every new row of data, you're going to have an output. Okay? Let's do it in code.